Okay, so we have just a little bit more to do with acids and bases. So you've done some titrations in lab, and what I'm hoping to get to is titration curves. Because depending on who you have for lab, you may have seen this, but we can use a titration curve if we don't have a good indicator for the acid and base combination that we're doing. Sometimes it's not as clear as doing vinegar and phenolphthalein. So having a titration curve can really help you see where those things are. And then I know a lot of you are interested in health fields. If you go on and take biochemistry, the titration curves have several points on them that are really significant for helping you understand buffers and how those acids are going to act within biological systems. So understanding what a basic titration curve will really kind of give you a head start for that first part of biochemistry. So I really want to get to there. Okay, so we were looking at the Bronsted-Lowry definition where we have the proton donor, the proton acceptor. And the real key thing on this is that we don't really have to have this system be in water. We mostly looked at aqueous systems. That's what we usually deal with in general chemistry. But sometimes you have acids and bases in organic chemistry that don't involve water because organic things don't always dissolve in water. So if we look at something like this, ammonia, we know ammonia is a base. If we have that in H2S, hydrosulfuric acid, it can accept a proton from the hydrosulfuric acid. So since it is the proton acceptor, it is the base. And since the hydrosulfuric acid is the proton donor, it is the acid. Okay, so as we said before, when we change definitions, we don't want to have anything that used to be a base now become an acid. We want it still to stick. And both of those would be the same thing if we put them in water. So as H2S is the acid because it gives up the proton, and H3 is still a base like you said it was. And you should absolutely know just off the top of your head that NH3 is ammonia. First of all, you should know its name. And second of all, you should absolutely know that it is a base. Anytime nitrogen is attached to a carbon, it is almost always also a base. We would call those amines. Okay, so we've talked about acids and how they behave. We can apply equilibrium reaction conditions to bases the same way that we can for acids. So if I have an acid-base reaction using this Bronsted-Lowry definition, something has to donate the proton, something has to accept the proton. So there's going to be both an acid and a base in both cases. Hope that is picking up my audio. Okay. All right. So in this system, and we looked at this on that chart, we had hydrochloric acid mixed with water. Now we said water could act as either an acid or a base. Oh, it's not advancing, darn. Water can act as either an acid or a base. In this case, is water being the acid or is it being the base? Remember, our definitions are the acid is the donator of the proton, the base is the acceptor. So water is the base, it is accepting the proton. Okay, and then HF or hydrochloric acid is donating the proton, so it is the base. Now, as a general rule, if you have ions, so our reactants here, this battery isn't working. Oh, well, this is completely useless. As a general rule, if we have a negative charge, those tend to act as bases, because the negative is going to attract that positive H plus. And if we have something that is positive, it tends to act as an acid because it's going to attract the OH, right? Or it's going to be ready to get rid of that positive charge. Okay, so either way, when we have an ion, that can be a clue. Now, that is not 100% of the time because of polyprotic acids, but it is a good indicator if you're trying to decide. Okay, so in this case, H2 is the base because it accepts the H plus. If we flip it around then, is the fluoride the base or is it the acid? Does it donate a proton or does it accept a proton? It accepts a proton. So fluoride is the base. And remember, ide is the ending we use for when it's an anion. So fluoride is F minus. And then H3O plus, what's the name of that ion? Hydronium. I wanted to put that on your quiz, but the quiz was too long. So hydronium is donating a proton, so it is the acid. Okay? All right. So we talked a little bit about conjugate pairs. The pairs are identical except for one hydrogen. So when we have an acid, its conjugate base will look just like it with one less hydrogen and the charge down by one because that proton has a positive charge. So in this case, the acetic acid, its conjugate is acetate. So remember, those are an acid and an ion that were on your list of things to memorize in Chemistry 111. So they're good to remember, but I will try and repeat those just to kind of get it into your brain. All right, and then always whenever we have water and hydronium, oops, that one did, oh, there it is. Hydronium is going to be one different from water because of that H plus. All right, we looked at that. We got that. All right, so let's look at reaction 4. Now here we have a situation where we have two negatives. So I said usually a negative is going to be a base, but the exception is when we're dealing with polyprotic acids. So a polyprotic acid, poly meaning many, has more than one hydrogen that can ionize. Okay, so a protic hydrogen is one that can come off. It will be attached to usually an oxygen, but in the case of the binary acids like HCl or whatever, it's the thing that's not that is not hydrogen. But if it is ever attached to a carbon, that hydrogen does not ionize. The carbon and hydrogen are very close in electronegativity. They're only different by 0.5. And that is not a polar bond. I mean, very, very slightly polar, but not very polar. And so that's not enough difference to be able to pull off that hydrogen, except in very extreme situations. Okay, so it's not real relevant right here, but if we take a look at this, this is from a polyprotic acid H3PO4, which would be phosphoric acid, and this is dihydrogen phosphate ion. So it could act as a base. It could pick up a hydrogen if it were an environment where there are lots of extra hydroniums. But if it's an environment where there's a lot of extra hydroxide, it can also give up that hydrogen. So it's listed in the column that is the acid column. So think to yourself, write down, what do you think, because it's going to be too complicated to say out loud, but try it for yourself. What do you think that conjugate base over here is going to look like? When I take this away, what is the base of this going to look like? How many hydrogens? How will the charge change? And then the hydroxide, we know that its conjugate acid just has one more hydrogen. So that's going to be what? You can say that out loud. Water. Yeah. So this is going to be water. All right. Is this what you predicted? Oops, wrong one. Is this what you predicted for the base here? One less hydrogen, the charge is more negative by one. Okay, let's try the next one. What is the name of H2SO4? That one we need to know. Sulfuric acid. The X are stronger than the Us's because they have more oxygens. Is that a strong acid or is that a weak acid? That one is a strong acid. For the oxoacids, a good rule of thumb is that if the number of hydrogens and the number of oxygens differ by 2 or more, this is different by 2, it's probably strong. The exception is HClO3. It is very strong, but it is not considered a strong acid. Okay, so H2SO4 and N2H5. So here's another scenario where these hydrogens are attached to a nitrogen. That's more polar than being attached to a carbon, but it's still not quite as polar as being attached to an oxygen. And so it's not quite as protic. So these usually are not very protic. Okay, so if H2SO4 is our acid, what is its conjugate base going to look like? So I'm not going to have you shout it out loud, but think about what that might be. And then think about what the conjugate acid of this is going to be. And this one's kind of counterintuitive to what I had said before. I won't give you confusing things like this one, but that's one where it's positive, but it's acting as a base. All right, you got in mind what you think those are going to look like? Is this what we picked for the sulfuric acid, HSO4 minus? So the charge goes down by 1, hydrogen goes down by 1. And then with this one, we increased the hydrogen and it became 2 plus. Okay, so there's probably somewhere in this solution some counter ions, maybe a bunch of chlorides somewhere that are helping with that. Okay, last one. Now, could this one also be an acid? If I mix this with, say, sodium hydroxide, that probably would be able to peel that off. But this is a weak acid. Okay, so this one was strong. This is now weak because this is negatively charged. Okay, HPO42 minus. So that's this one's conjugate base right here. So now it's over here. It's an acid, and we're mixing it with the sulfite ion. So think about what you think those conjugates are going to look like. You can imagine on your final exam having questions like this. What are the conjugates of each of these? All right, you got your mental idea of what these are going to be? Is that what you were thinking? Hopefully, yes. Okay. So what about if I have metal ions? So metals, we don't think of as having hydrogens at all. They can't really be proton donors. But we said, according to the Lewis acid definition, that they can accept a lone pair. Okay, so on ammonia, the ammonia can attach to it. And this creates what's called a coordinate covalent compound. So metals usually are ionic, but instead, these attach as if it's a covalent interaction with those lone pairs. So metals form what kind of charges, positive or negative? Metals are always cations, are always positive, right? So all of these in their ionic form, if I could drop the chlorides of them, because chloride's pretty soluble, if I drop the chloride of those into water, almost all of them are going to cause the pH to become more acidic. Does that mean the pH goes down or the pH goes up? Down. More acidic is down. What's my dividing line between acid and base? 7. Sometimes people think it's 10, but it's 7. Okay, so we looked at this before, but this is looking at strength of the particular acids, not just like individual like substances and things. And so we see at the top are strong acids and their conjugates, and down here we have our strong bases and their conjugates. So for the acids, we list molecules mostly at the top, but the bases, we list ions. So if these ions are attached to a group 1 metal, since group 1 metals are always soluble, those become the strong bases. So sodium hydroxide, sodium sulfide, sodium oxide, potassium oxide, all of those things for group 1. A lot of the group 2, but not all of the group 2 are going to be soluble. So I'll try to leave group 2 out of it. But if these are attached to group 1. Now, the opposite of a weak is a weak. That seems kind of weird. But that's because of our definition. So acids are going to partially dissociate. And so that means that the weak base is only going to be partial as well. Okay, so both of them are partial. One is partially dissociating, one is partially accepting that hydrogen. The opposite of something that is strong is negligible. What it means by negligible, it means it has very little impact on the pH. So I have over here, think neutral. When you see negligible, that means that ion is neutral. It doesn't really impact pH at all. Okay, so a strong acid has a negligible conjugate base, meaning a neutral conjugate base. So chloride ion, regardless of where it came from, doesn't really impact the pH. If it's from sodium chloride, if it's from hydrochloric acid, if it is from iron chloride, the chloride isn't really doing the pH. It is the other thing, the counter ion, that is impacting the pH. So the H plus is what causes that pH to change. In sodium chloride, we're paying attention to the Na. In iron chloride, we're paying attention to the iron. And this is really helpful because it means we can ignore chloride. Okay. So what we're going to be heading towards is what happens when I take a salt and dissolve it in water. Is the pH going to go up? Is the pH going to go down? And we'll have to put the ions separately to decide what's going to happen. So knowing that I can ignore things like chlorine is a good thing. So I can ignore chloride, but since HBr and HI over here are also strong acids, I can ignore bromides and iodides. Okay, I can also ignore nitrates and perchlorates. They are not impacting the pH. Now, the exception to that is a little bit the HSO4 minus. So the HSO4 minus, you'll see over here, it's negligible as a base, but it still acts as a pretty strong acid. Okay, so since it's polyprotic, it doesn't quite fit that rule of being negligible as neutral. Okay, if it's part of a polyprotic, then it's not negligible. But otherwise, the conjugates are neutral. Okay, and we can say the same thing about the bases. The strong bases have negligible conjugate acids. Okay, so if I think about NaOH, the conjugate of OH is H2O, water. I can also think about whatever the dissolving ion, those first row or group 1 rather, metals, the sodium, the lithium, and the potassium, all of those are going to be negligible as well. Okay, because we considered those to be strong bases, the sodium hydroxide, lithium hydroxide, rubidium hydroxide, potassium hydroxide. All of those first column, first group metals are neutral or not impacting our pH. In contrast, weak acids have weak conjugate bases. Weak bases have weak conjugate acids. Okay? So when I look at an ion, what I want to do is, if it is negative, add a hydrogen to it. If it is positive, add an OH to it. So to turn it into something that is neutral, and decide, is that thing that I'm looking at a strong acid or a strong base, in which case the thing that it came from is neutral? Or is it a weak acid or a weak base, in which case it is the opposite? It is the weak base of acid. So we're going to go through a few examples. Okay, so first of all, let's think about chloride. And I said this before, so hopefully everybody was paying attention. What kind of base is chloride? So we think about, from what I just said, let's add a hydrogen to it, HCl. We ask ourselves, is hydrochloric acid a strong acid? Yes. So if hydrochloric acid is a strong acid, chloride is which? A, B, or C? A, negligible or neutral. Okay. All right, so we said all group 1 metal ions are negligible because those are the ones that make up our strong bases, the hydroxides. In general, cations are going to be acidic. So aside from group 1, if you see your salt has some sort of cation attached to it, then you're going to assume that it's acidic. Now, like I said, there are some in group 2 that fit into that category. I think barium is considered to be negligible. I'll avoid asking about group 2. But if it's not a group 1 metal, assume that it's at least a little bit acidic. And anions tend to be basic, with the exception of if it's part of a polyprotic acid. So if there's an H out front and it's negative, it's probably actually acidic. It can act as a base, but if I have that attached to, say, a sodium where there's no, where the counter ion is not acidic, it's going to act as the acid. All right. So you see under here the word amphoteric, or sometimes you hear amphiprotic. This means it can act as both as an acid and a base. It can donate a proton, it can accept a proton. So our best example of that is water, right? Water can donate, water can accept. The counter ions of polyprotic acids, so the conjugates, I'm sorry, of polyprotic acid. So once I've taken one of the hydrogens away, these are amphiprotic. Now, in the case of the phosphates, I have 2 versions of that. I have it with 1 hydrogen, I have it with 2 hydrogens. Both of those are considered amphoteric or amphiprotic because they can donate their extra proton, or they can accept one to become less negative. It turns out ammonia is also amphoteric or amphiprotic. So in water, it's pretty much always going to be a base. But if I have it in a basic enough solution, if I have an environment where there's a strongly basic situation, it has extra hydrogens. And it is a polar bond, much more polar than the CH bond. So in very, very strong basic conditions, that extra hydrogen can be pulled off. And usually that is when we have ammonia as the solvent rather than water as the solvent. So you have liquid ammonia, you can pull off that hydrogen. All right, so let's consider this reaction. All right, which reactant is acting as the acid? First one or the second? The first one. It is giving up a proton. And so when it does, which is its conjugate of the 2 products? What's the conjugate base? The first or the second? The second one. It looks just like it with 1 less hydrogen and 1 lower charge. All right. And what is the name of the reactant that is the base? Ammonia. Yes, remember, this is what I told you need to know. Ammonia. And then you should also know its conjugate acid, which sounds very similar. Ammonium. Okay. So ammonium ends in the same ending that a lot of metals do. Chromium, lithium, sodium. Okay. So it acts like the ammonium acts like a metal cation in a lot of ways. All right. So we have H2PO4 minus is an acid. HPO4 2 minus is its conjugate base. But, so If one is weak, the other is weak, right? What about ammonia? Is that a weak base or a strong base? Weak. So all of our strong bases pretty much end in hydroxide. We said also oxides and sulfides. Sulfides are pretty rare examples, but if it's OH or just O, then we might have a strong base. So ammonia is weak and ammonium